It's just a short guts video of this 1 kilowatt high pressure mercury street lighting floodlight, which is something you don't typically see a lot nowadays with all the LED nonsense. But yeah, very, very simple inside. Also, another important thing to note, if you get a hold of one of these, they're typically 120 volt only. So they do not have quad tap ballasts. In fact, the ballast design of this thing is fairly interesting due to how it's implemented, because there's a whole buttload of jumpers on it, but those jumpers are all fixed. It's not anything that's configurable. What it's using is a pair of transformer windings down here, actually it's auto transformers, to generate the two, somewhere in the neighborhood of like 400 to 500 volt phases, or that combine to 400 to 500 volts, to supply the lamp and capacitor circuit, because this is a constant power auto transformer, so the capacitor is in series with the lamp. And so that's what two of those jumpers are, is they're just carrying over the 120 volt hot and neutral to both of these two windings. And then there's this jumper here, which is, oh no, this jumper here, which is coupling the end tap of one of those auto transformers to the waveform forming choke part of the ballast, although it also does sort of serve as a auto transformer winding, just one that's magnetically shunted down there with some laminations which are wrapped in this kind of paper stuff. There's the ballast part number, made in Hendersonville, North Carolina in January of 1993. And the lamp is, well, the lamp isn't in it right now, but is a Bath, New York made Philips from November of 1991. And yes, this is a fixture which could be converted to, say, like 1 kilowatt metal halide with a 240 volt capable ballast, but A, it would need a new photocell. And you can see that the photocell was wrapped up in electrical tape quite a while ago, because I just got these less than 24 hours ago. So obviously I did not do that. This fixture has, from what I can tell, no use in the field. It was probably shop spares that never got used, and then it was fitted with a plug for use as a work light. But looking at the condition of the lamp, I don't think this thing has had more than a few, maybe tens of hours of runtime. So it's effectively new old stock. And down there you can see the terminal block with fairly large terminals, because you'll see that a lot with these kinds of terminal blocks in street lights, where it could easily be wired up with something like 10 gauge or even sometimes 8 gauge wire, and so the terminal blocks or positions are quite big to allow for that. And then you can see it's mounted on top of the capacitor. And built by Curtis O. about 30 years ago. Another interesting feature, because of how big these how hot these fixtures run, is there's this kind of high temperature foam thing in the inside of the fixture door. That is a vent filter. So what it does is, because the fixture runs so hot, the air inside it expands, and it can just bleed out through this filter, and then when the fixture shuts off and cools down, air will get sucked back in there, because otherwise what can happen is, if the fixture is hermetically sealed, then that pressure gradient can often suck in water that's accumulated in certain parts of the filter, and so that's how you'll end up with fixtures becoming fish bowls, which is not good. And then there's this extra packing gland for if whoever's installing it is using a different size cable at the inlet. Because what this plate with a screw in it there does is it squishes this packing gland down onto the cable and forms a seal so that rainwater, in theory, can't get in. Note, in theory, because you can see that even with what little use this fixture's had, there's still a little bit of a puddle residuum right there. And another important thing of note is that there's this high temperature paperboard material that serves as a cover for the electrical wiring, just to prevent it from getting damaged by inadvertently rubbing on the inside of the fixture. Because these things are designed to be in service for decades, there's all kinds of time-related degradation, especially at quite high temperatures, that can happen that needs to be accounted for. Which, of course, you don't see in LEDs nowadays, but it's because the things are so failure-prone that, oh, we're going to be replacing the fixture in a couple of years anyway. And for those who need to know what it is, that capacitor is a 20 microfarad 580 volt cap. So it means that open circuit the ballast is going to be putting out at least 500 volts. Because quite often the capacitors in these things are run at somewhat close to their rating. Because the potential is going to go down in service as the lamp warms up, but high pressure mercury lamps only have, in the case of this, because the arc length is so long, probably 20 to 30 volts across it when it starts up. Of course, it's going to be on the order of, I think, 250 to 270 volts when it's actually up to full church. But, yeah, for that period, especially right after the main discharge is struck, the potential is quite low. As you can see, plus 3%, minus 3% tolerance, because this being a resonant RC circuit, that capacitance value is fairly critical. And the reason it says plus 3, minus 3% is because quite often capacitors used in power stuff can have asymmetric tolerances, especially things like DC bus capacitors, where all you care about is it have a minimum capacitance, and that's where you'll see things like electrolytics that have, say, a minus 20 but plus 80% tolerance or plus 100% tolerance, because if a capacitor is, say, 2,000 microfarads or 2 millifarads, it's a problem if it's below 1.8 millifarads. It's not a problem if it's 3 millifarads, because, you know, as long as you've got enough capacitance to do the job. But for this, the actual capacitance is quite important, because the value of this capacitor affects the end result of the drive current waveform, which in the case of a constant power autotransform ballast is actually a square wave with a peak at the start of each half cycle, which is why these ballasts are also often called peak lead ballasts, because there's a peak on the leading edge of each drive current waveform half cycle. And this is wired up with 12-2 cable, so ground is not fitted to that screw. But quite often these fixtures are mounted on brackets which are separately grounded, because the general rule with utility stuff, having worked in utility distribution for some years, is every metal thingamajig on the pole is electrically bonded to usually a number 8 bare copper wire, which goes to either a ground rod that's sunk at the base of the pole, or the ground wire is stapled to the butt of the pole and wrapped in this kind of a spiral pattern, and it's what meth heads really, really like to steal, because they are scum. And last but not least, there's the wiring diagram. Quite simple, actually. There's the incoming terminal block up there, photocell, socket, ballast, capacitor, and the lamp holder. And there's the photo control. It's a Fisher Pierce, made in 1992. Again, no UV fading on it, so this thing has not seen much of any outdoor use. And the reason for this electrical tape wrap over the window is to turn this into a kind of Jimmy Jackwagon shorting cap, because these photo controls, like most, they default to on, they fail on, so that way it's readily apparent that the photocell has failed and needs to be replaced. And also because the way most of these are constructed, especially these older ones, is there's a light dependent resistor cadmium sulfide cell and a heater, and the cadmium sulfide cell controls the electricity through and thus power dissipated by that heater. That's also why the photocells tend to be quite big and are mounted on heat sinks, because there's a period when the resistance of the heater is equal to the photocell resistance. That photocell can be dissipating, more than a watt, which is quite a lot for a photocell. And of course it starts out in the on condition. As the heater heats up, it opens a bimetal strip, and shuts the light off. And then when the sun goes down, cadmium sulfide cell resistance goes way up, heater power dissipation goes way down because current through it's gone way down, and bimetal switch cools down, closes the contacts, and light turns on. And this unscrews. Come on, you. Yeah, just straight on there. And October 1992, 1000 watt, 1.8 kVA, 105 to 130 volts, 50-60 cycle. Those numbers right there, that would be how the photocell would be dated. You'd see a paint dot right next to the year of manufacture, as well as the month of manufacture, but also the idea is you mark what month and year the photocell was installed, and that's why there are these areas so that you could put either a paint dot or usually like a scratch or a cut there with, say, like a screwdriver or a knife or something, just to mark when the photocell was installed for warranty and quality monitoring purposes. Although this one, of course, it wasn't marked with paint dots because it's printed on the label right there, October 1982, which is 31 years. And how the world has fallen so much in that time. And there's the end of the discharge tube, and virtually no graying. So this lamp has seen very little use. It's actually cleaner than a lot of newer Chinesium high pressure mercury lamps. So yeah. And there's the starting resistor, which is current limiting for the starting electrode, which is that little tiny thin one next to the main electrode, which is how a high pressure mercury lamp starts. Is there's a discharge that strikes between those two electrodes, which ionizes the plasma discharge tube, and it allows the main discharge to strike. And then there's just a little tiny, few milliamperes usually discharge between the starting electrode and main electrode thereafter. And this is also a way that you can tell that this is not a metal halide lamp, because in a metal halide lamp there would be a thermal switch that actually shunts those two electrodes together, because what can happen is you can end up with some of the halide dosing salts condensing on the end of the discharge tube, and any current that passes through that salt puddle or salt droplets between the main electrode and the starting electrode can cause electrolytic decomposition of the quartz and early lamp failure. And so there'd be that thermal switch, but because this is a high pressure mercury lamp which doesn't have that halide dose, you don't need to worry about it. Also, you can see the resistor that's actually constructed the way a lot of carbon film and metal film resistors are that you'd be familiar with from electronics, thus the somewhat familiar dog bone shape. However, this does not have an outer epoxy coating because due to the conditions inside the outer envelope of a high pressure mercury lamp, that coating is going to contaminate the gas fill, which in the case of a lamp like this is going to be nitrogen. It's nitrogen in most high pressure mercury lamps, but rarely you can find lamps which are designed for very low temperature service. Those will have a vacuum atmosphere. A vacuum atmosphere is also used in 40 and 50 watt high pressure mercury lamps just because nitrogen would cool the arc tube down too much. And some early phosphored lamps used a carbon dioxide gas fill because when blasted by the shortwave ultraviolet light coming off of the discharge tube, it gave off just enough oxygen to keep, I don't remember what metal it is, but one of the metals in the phosphor coating would change from, I think it's the +4 oxidation state to the +2 oxidation state, and it greatly reduced the phosphor efficiency. Having a very tiny trace of oxygen from the breakdown of the carbon dioxide fixed that and bumped the metal back to the +4 oxidation state, while at the same time there was never enough oxygen to risk damaging seals. Of course, that carbon dioxide isn't needed, as one last thing, for these, because this lamp uses a europium doped yttrium vanadate phosphor, which is what just about all phosphored high pressure mercury lamps have employed for the past half century plus, like close to 60 years now. The one exception being a blue producing phosphor, which was used in certain Iwasaki lamps for emulating moonlight conditions, and I would really like to get a hold of some of those lamps because those would be quite useful for certain niche high color temperature applications. And one last thing, there's the lamp etch. Philips 1000 watt H36GW/1000-1000DX. DX referring to the deluxe phosphor, which is the aforementioned europium doped yttrium vanadate. And then the USA, of course that's the country it was made in, that symbol which looks like the electrical schematic symbol for an antenna, or certain types of antenna, that is the factory code for Bath, New York, and the 1L-1 is November 1991, and I haven't figured out what the -1 means yet. But yeah, that the Bath, New York lamp works closed down in early 2014. And thereafter, these lamps are typically made in... These lamps would usually be Chinese, which... Some of the Philips Chinesium discharge lamps are okay, but still not as good as the ones that were made here. And that factory actually used to be owned by Westinghouse. And one final last good thing about these fixtures: captive screws. Because this comparatively tiny screw would be major pain in the dick. This thing falls out and you're 30-odd foot up in a bucket truck installing the thing or maintaining it. And one last thing is note the square nut. It's very common to see nowadays on utility stuff because you can apply a lot more torque to this than you can with a hex head nut or bolt under, especially the 200-pound gorilla conditions of a lot of utility stuff.